So what if I told you you could take absolutely any image you have, like this one on the left here, and turn it into a really neat 3D background that responds to mouse movements and creates some dynamic energy on that photo? Well, that's what we're going to learn how to do using React 3 Fiber and a little bit of AI trickery to generate a depth map. So the first thing we're going to need before we get into React is a depth map for whatever image we want to use in our background. Now, there are apps on some cameras, phone cameras specifically now, that can give you a depth map directly using the LiDAR that's built into some modern phones. But what if you just have some random image from online or that you took with a regular camera and you don't have a depth map for it? Well, there are now some really cool machine learning models that can generate depth maps for you. The one that I've been using is this MiDAS model that I found on PyTorch Hub. And it is based on this really cool paper towards robust monocular depth estimation, mixing datasets for zero-shot cross dataset transfer. And this particular paper has all the source code published for it for the PyTorch model, and you can even run it directly on Hugging Face, which is a place to host machine learning models. I will post links to all this stuff so that you can use it. You can definitely take this GitHub library, clone it, and run the PyTorch model yourself on your computer. But you have to have all of your CUDA stuff set up a certain way and your Python environment set up a certain way and have a good enough video card. So for the purposes of doing this tutorial, you really can just use the Hugging Face UI here and select the image that you want to use to create a depth map. You'll see I've already generated my depth maps, but just to show you how easy it is, if I select my image and hit submit, just takes a couple of seconds, and when it's done, you'll have a cool little depth map. So you just go ahead, save this, make sure you have your original color image as well, put them both in the same place, and we'll get started using them in React now. So now let's go back to the code and switch out the image to the image that you just generated in Hugging Face. So the first thing you're going to need to do is click on the link to this code sandbox that I'll put in the video description. Once you do that, you'll end up in a view just like this one, where you have the preview on the right and the code on the left, in case you've never used code sandbox. And once you're here, you'll be able to click this fork button, which will create a copy for you that will live under your account. If you don't have your own account, it'll prompt you to create one. So go ahead and go through that process. Code Sandbox is awesome, and I highly recommend signing up. All right, so once you have a forked version of the project, you can change the name to be whatever you want to have it be, and then now you can edit your own copy of the project. So the first thing we're going to do is upload our static images that we generated to this public directory. So if you select the public directory, you'll see this up arrow here, which is the upload files link. And then you can select the pair of images that you have, both the color original image and the depth map image. This is a new pair that I just generated a minute ago, a picture of a rock out in the ocean and its accompanying depth map generated from the MiDAS model. So select both of those and click open. And don't forget, those are the two images that you generated, so the names are going to be whatever you named them. And once you have the images, I'm going to show you just how easy it is to swap this effect out between any image that you have. The only two lines you need to change the images are line 16 and line 17. So you'll see this texture variable and this depth map variable. They both use this use texture hook, which is being imported from the Dry package. Dry is a wonderful library for React 3 helpers that just make things a whole lot easier. And to load a texture, all you need to do is call that hook with the path. So this path is the current image we're using. If we want to switch to our new image, we just need to change that name to be whatever our new pair of images are named. In my case, it's color-ocean. At least I thought it is. Okay, and then once it refreshes, you'll have your new 3D effect. All right, so now that we have the textures loaded, let's talk about how we use them to create the 3D effect. Now, to apply a texture, we know that we're going to need some geometry to apply the texture to. And in our case, that's just this plane, and it's the only piece of geometry in the whole scene. If you look at this top level app component, you'll see we're only loading one thing in the canvas, and that is this model. And the model is just a plane. So our plane has one interesting thing about it, which is that it's being scaled to fit the viewport width and height, which we're getting by using the use3 hook and accessing the viewport. And that's just a convenient way to make the geometry for our texture fit the whole screen. If I were to change this, we could see it respond just like any normal plane would. We can control that however we want to. We'll just leave it like this. So now that we know that we're just working with one simple plane that we're going to texture, well, what exactly are we texturing it with? We're texturing it with this pseudo 3D material. And the pseudo 3D material is a custom shader material that we are creating and extending into the React 3 Fiber namespace. And when I say extending into the React 3 Fiber namespace, what I mean by that is, look how we're using this component name here. We're not actually importing this anywhere. There's no place where we're like importing a component called pseudo 3D material. Rather, we're extending React 3 Fiber on top of its existing components. So this is already a thing. Like whenever we try to, for example, use like a, say a Lambert material, mesh Lambert material, those components are available to us without importing them as well. And that's because we know that React 3 Fiber is mapping them all from the Three.js classes. Well, shaderMaterial is a custom Three.js class that we're going to create using our very own shader code. And extend is just letting us give it a name so that React 3 Fiber can find it. Basically, to prove that point, if I change the name and then try to refresh the screen, we're going to find an error message here saying pseudo 3D material is not part of the 3 namespace. Did you forget to extend? Well, I mean, not exactly, but we did give it a wrong name. So we can change that test material, or actually even better, let's use that test material. And here's our scene again. So we know now that this component is finding this shader material. All right, so now it's time to talk about shader material. This is the function that's doing all the work for us. Shader material takes 3 arguments. The first argument is an object, which is called the uniforms argument. And uniforms are variables that are provided to shaders, more or less. Like, let's just think of it that way. All of these are ways of providing data to the shader. Really the only way of passing, well, it's our best way of passing in external values. So we're passing in 3 external values: the mouse coordinates, with a default, by the way, of 0, 0. And the mouse coordinates are a 2-dimensional array. That'll come to be important later. We're also providing something called the U image and the U depth map. Now, this is where our textures are coming from. So the textures don't change frame to frame. They're constant throughout the scene. So we're just setting those as props on the material. Like we know that this image and this depth map are always the same. But the mouse value changes, right? So when I move the mouse, the geometry is not actually changing. It's our texture that's responding to the mouse position in some way, which we'll see in a minute. But for that to happen, we need to actually reset this U mouse value every time that the mouse moves. And the way we do that is with the use frame hook. So the use frame hook is just a function that runs every time the frame is calculated. So this is mostly controlled by like request animation frame and the browser API. So we don't need to think about this, but just know that this is running constantly, this function, and it's resetting this value based on where React 3 Fiber is saying the mouse position is, but also with a modifier. So we're passing in the mouse value times 0.01. And what we're saying there is make the change a lot smaller, compress it. And why are we doing that? Well, because if it's one, if we just don't have a multiplier, this thing like shifts way too much and looks like crap. So the value we want to use is sort of dependent on our own aesthetic sense. So you can play with this and change it and see what results you can get. Like if you want a crazy glitchy effect, feel free to just leave it as 1 and you can make like a weird, almost like a data mosh effect on the image. Nothing wrong with that. But yeah, so the important thing is that this is changing the uniform on each frame. Okay. So now that we know that we're passing in the 2 textures and the mouse value, what do we do with them? Well, we use them in our shaders, and we use them specifically in the fragment shader. The fragment shader is the shader that actually calculates the color of each pixel that we're going to render as the texture of the plane, if that makes sense. You can think of the fragment shader as a function that gets passed all of the coordinates of the plane itself. So like the top left pixel in the plane might be 0, 0, and the bottom right is going to be, whatever the size of our viewport is. Let's just pretend to keep our math simple that it's 255. So let's say that we're rendering a plane on the screen, just a flat plane, it's not moving. Let's say this top pixel is 0, 0, and this bottom right-hand corner is 255, 255. Okay, now those are coordinates on the plane, and the way we can store those coordinates are really the UV value here. Now, this first shader, or rather the second argument, is the vertex shader. Let's not think about the vertex shader. I don't want to get confused by talking about it. It's not important to this project, but just be aware that in the rendering pipeline, first, all the data gets passed to the vertex shader, which calculates a bunch of metadata about the vertices. But then all of that gets passed along to the fragment shader, which it actually calculates what color to render on the screen. So the only thing we're using the vertex shader is to get the UV, which is the coordinate of the plane that we're currently working on, and passing it through to the all-important fragment shader, or this whole string here. This is the fragment shader, okay? The fragment shader, we need to think of this as a function that runs on the input of an X and Y coordinate, and it outputs a color for that specific XY coordinate. In fact, you can think of the return type of this shader as just being a color, or specifically a vec4 data type. A vec4 is used to store colors because it stores an R red value, G green value, V blue value, and an alpha value. And in that way, you can store any color, any RGB color. So what we're rendering on the screen here is just a vec4 that has been calculated by running this shader function thousands of times. Like, this shader function has to run to render every single pixel on the screen. So the pixel up here in the top left, 0, 0, it gets run. It gets past this VUV value from the fragment shader of 0, 0. And don't forget, it also gets past all of our uniforms. These are the inputs: our current mouse position, the entire color image texture, and the entire depth map texture, and the UV coordinate. So to render this pixel on the top left screen of the screen, the very top left, that's what we get in. Okay. Now, lines 42 through 46 are just declaring the variables that we're going to use. Line 48 is the actual function body that's applied. So let's start doing the calculations to generate the texture. First thing we need to do is actually load the pixel in the depth map for our current active pixel in the UV map, where the UV map is a position on the plane. So for the top left pixel in the plane, we want to also get the top left pixel in the depth map. And we do that by calling the texture2D GLSL function, which is just know this is a function provided by the shader language. I will link to a bunch of resources about shaders because we just don't have enough time to get into all the details. I'm trying to just talk about what's necessary to make this effect work. But texture2D loads a color, a vec4, from a sampler2D variable, which this is being provided by us by React 3 Fiber. It's automatically providing this depth map because we loaded it as a texture here and passed it in as an argument or a prop. Okay, so it's available for texture2D, but we're just grabbing one pixel out of it. So we give it the coordinates that we're currently working on, 0, 0, and what we get back is the color of our texture map. So in our case, this image for this pixel way up in the top left. So it's some shade of gray. I don't know exactly what the values are, but let's say it's like 50, 50, 51 is the vec4, where a vec4 is a 4-number array representing the red, green, blue, and alpha coordinates. So we know now that we have a value for the depth map. But then we only care about one of those values. So we're going to grab just the green value out of the color and store it in a variable called parallax which is short for parallax multiplier. Okay, we'll get to why in a minute. So now we have a parallax multiplier that is some number. Next, we multiply the parallax multiplier by the mouse coordinates, which are a vec2, where vec2 is some two-dimensional array. When the mouse is in the very center of the screen, it's 0, 0. When it's in the top left, maybe it's like negative some. Well, it's probably negative something and negative something else. We don't need to know the specific numbers. Just know it's some negative number. And then if it's like in the bottom right, it might be two positive numbers. And that's changing as we move the mouse, right? Okay, so what that means is we end up with a new vec2, which is some parallax value where pixels that are closer to the camera, like this cliff in the bottom, are higher than pixels that are farther away. But the overall parallax is dependent on how far from the center of the screen our mouse is. But again, closer pixels are even bigger. And this is two-dimensional, right? So we have a parallax value for both the x and the y coordinates. Okay. So now that we have this parallax value, we need to use it to power our 3D effect. And the easiest way to visualize how that's happening is to remove it for a minute. So this variable we declared only gets used one place. We use it by adding it to the same UV that we used when we were loading the depth map color to our loader for the color image. So that means when we load the color image, in theory, like for a normal texture loader, we could load this without parallax. And if we load it without parallax, really what we're saying is just do a one-to-one mapping between the texture and the plane. So this is just a normal image now. No effect, nothing. And really all you have to do is add that parallax value back to get the effect back. And the reason that works is because now instead of loading the 0, 0 pixel in the texture for the 0, 0 coordinate on the plane, instead we're loading some different pixel from the image to render as 0, 0. And the pixel you load is farther away if you have a more if you have a closer pixel. So like I don't know if this is making sense completely, but so when I have a higher parallax value, the pixel I load from the texture might be like a pixel 10 to the right on the actual image. And we're kind of shifting them around to create the effect. And then by storing that in this original value, what we're doing is we're just storing one single color and then returning that. And that's how the effect works. That's really all there is to it. It's kind of a trick to shift pixels around in the color texture depending on how light or dark that corresponding color in the depth map is. Now again, this might not make 100% sense to you until you learn a little bit more about shaders. I hope that it did though, and I hope that you go and dig more into shaders to get a deeper understanding, because this shader material is going to be so powerful later. You don't need to just use it to make this effect. You could do anything. You could like invert the colors. You can do like blending modes, and you can do like generative sort of like dynamic effects based on math functions like sine waves and pretty much anything you can imagine. It's such a powerful skill to learn. So again, I'm going to put all these notes in the video or in the video description, and please dive into it more. The world of uniforms and shaders is really cool. So it's been fun talking to you about this. If you make any cool projects, please post them in the comments. I'd love to see them. Bye.